Okay, we are going to talk about a really new kind of way to think about equations. We're going to talk about parametric equations, and you probably haven't seen anything like this before, and hopefully you think they're really fun. All right, so let's think about, for example, if we have like the Earth circling the sun, something like that. So we've got an object moving through space, and we could describe this, for the most part, we could describe this as a circle, right? Or it's really an ellipse or whatever, but let's just pretend it's a circle. All right, so the Earth is circling the sun, and we could describe that with a function like we know how to write the equation for a circle, right? And we could write it sort of as, it's not really going to be a function because it's not going to pass the vertical line test, but we could write a relationship between x and y, right, to describe this motion. But is that really what's happening? Is the y position, if we were going to draw an axis here, is the y position of the Earth really like a function of the x position of the Earth at a given time? No, right? They're related. We could write an equation that relates the x and y positions, but the y position doesn't depend on the x position, right? What do they both depend on? They really depend on a third variable, time, right? As time passes, the y position of the Earth is going to depend on time, and the x position is also going to depend on time, right? So that's what a parametric function allows us to do, is to say, okay, we have two variables, x and y, that are both dependent on a third variable, almost always time. Okay, we're going to call it t. In this, this is just one section, kind of an introduction to the idea of parametric equations. We're always going to have x as a function of t and y as a function of t. Okay, so there's this third variable we're bringing in, and we're calling that the parameter. So here's the definition of parametric equations. Suppose t is a number on an interval. The set of ordered pairs x of t and y of t, where x is a function of t and y is a different function of t, forms a plane curve, meaning like some shape in the xy plane, based on the parameter t. The equations f of t and g of t are the parametric equations. Okay, so let's make this less abstract and do an actual variable. All right, so let's say we have this equation, y equals x squared minus 1. So just in the olden days, before you knew about parametric equations, we could think about this as there's going to be a parabola that is opened up, shifted down by 1, right? But what if we want to parameterize that curve? Okay, so here's what that's going to look like. They're telling us what one of the parameters is, one of the equations, one of the parametric equations. They're saying let x of t equal t. All right, so here's one of our equations, x of t equals t. All right, based on that, if x of t equals t, then what's y of t going to equal? Well, we could just write that as t squared minus 1, okay? Not too tricky so far. All right, so now we could make a table, right? We could choose some t values going from -4 to 4. And if x of t is just t, then, that's pretty easy, right? X of t is just going to equal the t value. And y for each of these t values we could evaluate. So y of -4, we plug it into this equation, and we get that it's 15. When t equals -3, y of -3 is going to equal 8, and so on, right? We could fill in this equation, fill in this table. Now notice, well, okay, so here's our table. So for a given t value, we have an x value and a y value, -4, 15. If t is -1, we have a point -1, 0, right? And so forth. And we could plot these like this. Okay, so this is actually a little bit tricky not having these on the same slide. But let's say if t equals 1, okay, if t equals 1, we're going to have a point 1, 0. So let's look over here. The point 1, 0 is going to happen when t equals 1. Okay, so here's our parameterized curve. Okay, so that happens when t equals 1. What about if t equals -3? Let's see, our point is -3, 8. So whoops. Let's look on our graph. -3, oh, whoops, wrong one. Right? It started up here. And as t gets bigger, our points are going to move along this curve. So you'll notice we have these arrows. Okay, this is just the graph y equals x squared minus 1. So it looks very similar, which we'd expect. But now we have this new element. We have a direction along this curve that our points are moving. As t gets bigger, we are moving along this curve in this direction. Okay, and we can see that because, let's see, like if t is -1, we're at -1, 0. Whoops. So right here, right? If t is -1. And then if t is 0, we're at 0, -1, right here. And then if t equals 1, we're here. So as t gets bigger, we are moving in this direction along this curve. So you can see how this could be very useful for modeling things that are actually moving, like, you know, the Earth moving around the sun, for example, right? It has a direction along that circle that it's moving in. And if we use parametric curves, we can capture that. Okay, we can, so that's the idea. As time progresses, we're moving in a direction along this curve. Whereas just with our regular rectangular parabola, we have the same curve, but we don't have any sense of a direction along that parabola. Okay, so let's do another example. Find a pair of parametric equations that models this graph using this parameter, plot some points. This is going to be very similar. They tell us the x of t equation, and it's just the straightforward x of t equals t. Now this is also a parabola. Looks like it's reflected, right? So it's opens down and is shifted up by 1. So if this is our x equation, our y equation, we're just going to say, okay, well, everywhere there's an x, I'm going to put in a t, and I'm going to get 1 minus t squared. Okay, so those are my two equations. And I'm going to do a similar thing. I'm going to make a table. So here's my different t values, and here's my x of t values, and here's my y of t values. And then I can plot them. So for example, -3, -8 is when t equals -3. And then if t equals -2, I'm here at -2, -3. If t equals -1, I'm at -1, 0, right? And so on. I can plot these points and they have an order. As time passes, as t gets bigger, we're moving along this parabola in this direction. Okay. All right, so let's do a different kind of a problem here. All right, so what if we have an object that travels at a steady rate along a straight path from this point, -5, 3, to this point, 3, -1, in the same plane in 4 seconds. The coordinates are measured in meters. Find parametric equations for the position of the object. All right, so let's just think about what's going on here. We have a point that's starting at -5, 3. So it starts here, and it goes to 3, -1, to this point. And it goes in this direction. Starts here, ends here, in 4 seconds. Okay? So what we want to do is we want to find two equations, x of t and y of t. Well, what's happening? We're going from -5 in the x direction. Let's think about it. We're starting at -5 and we're ending at 3. -5, 3, and this is 3, -1. So in the x direction, we're moving from -5 over to 3 in 4 seconds, and we're starting at -5. So how could we write an equation for this? Well, how fast are we moving? What's our slope in the x direction? We're moving at a rate, if we're going from -5 to 3 in 4 seconds, that's 2 meters per second times t, and we're starting at -5. So let's just check this out. If t is 0, where our x value is -5. If t is 4, we're at, let's see, 2 times 4 is 8, minus 5 is 3. Yeah, that gets us there, right? Because we're moving along this line in a steady motion. So we can write in the x direction, we can write it as a linear equation. So maybe think for a minute, what do you think our y equation is going to look like? We're starting at 3, we're starting at 3 and we're ending at -1. So it looks like we're starting here and we're ending here. In 4 seconds, we go 4 units. So that's going to be our rate in the y direction is -1 times t, and we're starting at 3. Those are 2 equations. I could write those I could write 2t minus 5, and I could write this as minus t plus 3. So this is our x position as a function of time, and this is our y position as a function of time. Okay? Okay, and that's what they wanted us to do, is just find the parametric equations for the position of the object. And let's look, so here, once we found these equations, they plug in different values for t, 0, 1, 2, 3, 4, right? We're starting here at -5, 3, and we're moving at these different points along the way and ending up at 3, -1. And we could look at these 3 different graphs, okay? Here is the graph of, so we're starting here at -5, 3. Don't know why they didn't extend it all the way there. And we're ending at 3, -1. Okay. So this is the graph. We're starting at this point, ending here. And this is our position in the x direction. We're starting at -5. So this is a graph of our x of t. We're starting at -5 and we're ending at 3. From 0 to 4, we go from -5 to 3. And here, if this is our t-axis, if it's starting at 0. So when t is 0, we start at 3. And then by the time that t is 4, we're down to -1. Okay? You don't really need to graph these. Don't let these confuse you. Okay? We're just trying to match this graph. But if you wanted to think of x of t and y of t independently, they would look like this. But together, so t isn't really on this graph anywhere, is it? This is still just the x-axis. This is still the y-axis. T is like hovering above. It's out of the picture, but it's giving us the direction that we're moving along that line. Okay, so that is if they give us either an equation or a description of motion like this, those are some ways that we can parameterize those equations.